Hi, for the course 19 MA 206 Logic and Combinatorics, we are in Unit 1 Sets and Functions. So let's get on to the presentation. So before starting, let's have a look at the course outcome. Construct the class of functions which transform a finite set into another finite set which relates to input and output functions in computer science. So the first and foremost thing is relation. How do I define a relation? A relation, capital R, from a non-empty set, capital A, to a non-empty set, capital B, is a subset of the Cartesian product A cross B. So we have two non-empty sets, which are A and B, and there is a relation between this A and B, which is a subset, and it's denoted by the Cartesian product of A cross B. The set of all first elements of the ordered pairs in a relation R from a set A to a set B is called the domain of the relation capital R. So it is in order from A to B. So the first set of elements with an ordered pairs. This is how we define a relation. The set of all second elements in R from set A to set B be called the range of the relation capital R. So first we have seen the domain, and the next is the second set of elements. So those elements are called as range of the relation capital R. Now what about B? Now we will be insisting only on the set A. So what happens to B? The whole set B is called the codomain of the relation capital R. Note that the range is always a subset of the codomain. So this is how we define relation. So relation is represented by the Cartesian product of A cross B, and domain, range, and B is called the codomain. And let's look at the types of functions. A function f from x to the set y is defined to be one-to-one, other words injective, if the images of distinct elements of capital X under f are distinct. Distinct in the sense different. So when I take two elements x1 and x2 which belongs to the set X, we see that f of x1 is equal to f of x2, which implies x1 is equal to x2. This is called one-to-one. One element of x will be mapped to one element of the other one. The second type of function is called onto function. In other words, it is called a surjective. It's defined by a function f from x to y is said to be onto if every element of y is the image of some element of capital X under f, that is, for every y in capital Y, there exists an element x belongs to capital X such that f of x is equal to y. Third type of function is both combined, one-to-one and onto, which is called as bijective. So one-to-one, we had the name injective. Onto, we give the name surjective, and one-to-one and onto together, it is called as bijective. So it's simply defined as if f is both one-to-one and onto, it is called bijective function. So again, I repeat, there is one-to-one function, onto function, one-to-one and onto, which is also called as bijective, surjective, and injective. The next concept is the composition of functions, which means that composition in the sense combining of two different functions or maybe three different functions. Okay, so let f take two functions here. F is defined from the set A to B and takes the second function g, which is from B to C. Be two functions, then the composition of f and g denoted by g composition f is defined as a function g composition f which is from A to C, given by g of composition of f of x is equal to g of f of x for all x belongs to A. So this is how I define for two functions f and g. Now what is invertible function? A function f from x to y is defined to be invertible if there exists a function g from y to x. So first we define a function. We have a function which is from x to y and we call it as invertible only when there is another function which exists where is from y to x, such that G composition of f is equal to I of x and f composition G is equal to Iy. The function G is called the inverse of f and is denoted by f inverse. A function f which is from x tends to y is invertible if and only if f is a bijective function. So invertible function for three functions: f function, g function and h function. So f is from x to y, g is from y to z and h is from z to s are functions. Then h composition g composition of f is equal to h composition g of f. And the fourth condition is, let f from x to y and g from y to z be two invertible functions. Then g of f is also invertible. That is, G composition F inverse is equal to F inverse composition G inverse. This is how we define. And let's practice an example here. So what is it asked in the question? So let A is equal to 0, 1, 2, 3. So A is a non-empty set containing 4 elements. And a relation is defined. That is, the first presentation started with the first concept of relation. So define a relation R on A as follows. So how am I defining a relation there? 0 is mapped to 0, 1 is mapped to 1, 0 to 3, 1 to 0, 1, 1, 2 to 3, 0 and 3, 3. This is how the the relation. So now we have to check whether this relation is reflexive, symmetric and transitive. So there are three things: reflexive, symmetric and transitive. So first, R is reflexive and symmetric but not transitive. Since 1, 0 belongs to R and 0, 3 belongs to R. You see that where is 1, 0 here? 1, 0 belongs to this R and 3, 0 also belongs to R. Whereas 1, 3 does not belongs to R. That is, this is from 1 is mapped to 0 and 0 is mapped to 3. Then I should say 1 is mapped to 3. But that is not happening. That is not mentioned here, or that is not given in the relation. Therefore, transitivity is absent here. So example 2. Let the function f from R to R be defined by f of x is equal to 4x minus 1 for all x which belongs to R. Then show that f is 1 to 1. So how do I prove this? For any two elements. So whenever you want to prove some relation or something like that, you just take a sample of two elements, random pick. So it can be x1, x2 which belongs to R, such that f of x1 is equal to f of x2 we have. So how do I define x1? For 4x1 minus 1 is equal to 4x2 minus 1. So just cancelling out this 1 on both the sides. So you'll be landing up with 4x1 is equal to 4x2, which further implies x1 is equal to x2, which says that, which shows or which is very clear that f is 1 to 1. Thank you.